Day 12, AP Physics, page 313, problem 62. I'm calling the bullet, which is still in the gun as pictured by the blue blob there, as mass sub 1, mass 1, and the block as mass 2. The block is, after the bullet's been fired, it's going to cause the block to go from position A to position B, or through a height of what I'm calling h. We need to find h in terms of the masses and the velocities of the particular bullet in particular. So this is a classic conservation of energy, conservation of momentum problem. I'm going to sort of do the problem backwards. You pretty much have to do it this way. The GPE at location B for the block with the bullet in it, I forgot to show the bullet in the block after it's been fired. So there's going to be a bullet lodged in this block number 2, which will be the sum of the two masses actually, at point B. So due to the conservation of energy, the GPE at location B of the two combined masses equals the kinetic energy at location A after the bullet has been embedded into the block and it's starting its way up. That's that's after the collision. It's after the bullet has been lodged into the big block. Bottom line, we have, and I'm doing a generic statement here right now because it's MGH, where that M there stands for the two masses together, equals 1/2 mv squared upon launch. And once again, that's the two masses together. So that both of those are the combined masses after the bullet has been fired into the block and the block starts upwards. So those can be canceled. All right, let's rewrite this for V. V squared equals 2gh. You've probably seen this before for other conservation of energy problems. And V is the square root of 2gh. And it looks like we might be done with the problem because we have V in terms of g and h. But this V here, that in this expression or this equation, is the velocity of the two masses combined. What I want is the velocity of the bullet by itself. So that's not the velocity I want, so it's a little bit, you gotta be a little bit careful here. Let me use another diagram to show now the conservation of momentum. So over here on the right I have the conservation of momentum situation at location A. So we have the location A before the bullet hits the block, just before it hits the block. So I have my little mass 1, the little blue dot is the bullet. Just before it enters the block, it has a velocity v sub 1, which is very great. And it has momentum then. So P1, the momentum before the collision, is solely due to the bullet, M1 V1. Alright, well, that has to be conserved after the collision on the right hand side here, but just immediately after the bullet embeds in the block. So you should have the bullet in here somewhere. It's mass 1 plus mass 2. So that says A after. The location A, just after the collision, we have P sub 2 equals the combined M sub 1 plus M sub 2 times V sub 2, which is the velocity after the impact. So those two quantities are equal to each other. In other words, P sub 1 equals P sub 2, conservation of momentum. This is an inelastic collision, so there will be some heat loss, some kinetic energy or mechanical energy lost. That is, it's an inelastic collision, so kinetic energy is not conserved. If it were a bouncy, elastic collision, you would also have the additional kinetic energy conserved as well as the momentum conserved. Okay, let's continue over here on the right hand side, symbolizing plugging in for P sub 1, momentum 1 equal to momentum number 2. That looks like this. M sub 1 V sub 1 equals M sub 1 plus M sub 2 times V sub 2. And let me do a little bit of fixing over here in the middle with the conservation of energy statements. I used the generic V that is, in my notations now, it's V sub 2. I can add that in here, V sub 2, V sub 2. That represents the velocity of the combined block with bullet in it. Going back to the right, solve for V sub 2. V sub 2 equals M sub 1 times V sub 1 over the sum of M sub 1 plus M sub 2. Alright, that's a plus right there. I'm going to take that and plug it in over here on the left. So I'm going to take that, plug it in for that, and I'll let you finish it off with the algebra. It's a little tricky, but not too bad. Plug it in, solve for V sub 1. Then you'll have your equation with the expression for V sub 1 in terms of the masses and the height, and then gravitational constant g. Once you have that all done, then you can actually plug in the numbers they give you in standard units to figure out the muzzle velocity, the firing velocity of that particular bullet.